Okay, how's everyone? Okay, so today we have this is considered as lecture number 9, and we are 1 week behind because of last week. So, what I will do for this week, tomorrow we will have the quiz, a short quiz. Then we will continue having replacement for one session tomorrow. So no tutorial, but we will cover one session for the lecture that we missed last week. Okay, so I hope you all have watched the video last week. That is the introduction of neural network. Before I proceed, do you have any question? No. Okay. So what I will cover today called perceptron. So perceptron is one of the variants of neural network. So they possess one of the simplest neural network architecture. So perceptron is used for prediction. Um, if you recall back, the prediction function is the function that predict what the output should be given the input. So this is during the training where we provide the input and also the sample output. So when we have a new unseen data, we will be able to predict what is the output of the new unseen data. Okay. So we also have looked at the linear function, which are commonly used as a prediction function. We call it linear function because we use a line to separate them, or a piece of paper to divide the positive and also the negative samples. So when we talk about linear, we will have a general form with k variables. So k refer to the number of variables that you have in your datasets. So given the input here, this is your input. So this is a function that will map to the output of your dataset. And this is your input here, depending on what is I. And this is the weightage of your variable xi. And this is the values or bias value that is used to adjust in order to minimize the mean square error. Okay. So when we simplify this, we will have something like this, in which we have a matrix. So we will have the matrix M here. Okay, so this is what we want to estimate. So during the training session, we will try to estimate the weightage of individual variables that we have here, so that it will minimize the mean square error. Mean square error refer to the differences between the actual values and the predicted values. So for instance, this is regression. Regression is a problem in which you are trying to draw a line that will model your numerical data. So this is in the XY data set. You have X and Y, okay, two-dimensional data. So the line is used to draw the trend that you have for your X and Y. We also have this classification. Okay, so the function of the classification is to draw a line that will separate the instant of positive and negative class. So this is for the simplest basic algorithm. So you are trying to find a line that will optimize the separation between the red square and also blue the blue cross. Okay, so where this is your positive sample and this is your negative sample. Okay, so that is the main function of linear function, which is try to divide the positive and negative and optimize the accuracy. So linear classification, for linear classification, a linear function divide the coordinate space into two parts, positive and negative. So this means that for two classification or two symbols, positive and negative, we call it binary classification. But if you have more than two, it's called multi-class classification. Okay, and for the this is also called conventional way in which we consider them as positive class and negative class. Okay, so if we look at the formula that we have, we will consider that the output for your function would be -1 or 1. So this one refer to negative samples, and also this is positive samples. Okay, so the linear threshold unit classify an example X using the following classification. They say that if the output is positive, so we predict them as positive sample. If the output is negative, we predict them as negative. So this is 0 or positive. So remember that this is the function that we have simplified just now. Okay, so we will look at the signage of your value here. If the value is 0 or positive, 0 or greater, we will predict the output of Y to be 1, positive sample. So that's why it's very important for us to optimize the formula that we have here. So we have the input here. So during the training, basically we are estimating the best value for all the weightage of the variables and also the bias as well. Okay, so we will refer to this formula. Okay, so for all the variable that we have, we need to sum up them and we look at the signage. If they are greater or equal to 0, so we are saying that they are positive sample. If they are less than 0, so we are saying that they are negative sample. So very simple one, linear function. So when we look at this graph, we have negative and positive, right? So our task is not our task. The model is trained, and during the training, we will optimize where is the position of this blue line. So it could be up here, or we can move them down here. So the objective of moving the line is to make sure that when you have new unseen data, they will be correctly classified as negative and positive sample. Okay, so when we have the line here that separate positive and negative, we only look at the signage. So that's why if we look at this one here, this is your line formula. So whatever above here would be considered positive. Whatever below here is considered as negative. Okay. So we only look at the sign, not the size or the values of the function output that we have. This is for the prediction. Okay, so you see this neural network has been started being investigated in 1958. So they say that having told you that the giant digital computer known as IBM 704 and how it has been taught to play a fairly credible game of chess. So we like to tell you that even more remarkable machine, the Perceptron, which is which, as its name implies, is capable of what amount of original thought. The first Perceptron has yet to be built. So they started to investigate this since 1958. So today is 2025. So we have 42, 25, 67 years ago. Okay. So this was introduced by Rosenblatt in 1958. The goal is to find separating hyperplane for separable data. So they say that this is for the linear function only, because in 2D we are looking at the line that separate positive and negative. If we have 3D, we are looking at a piece of paper that will separate the positive and negative. But in the four dimensional, we cannot imagine. So, but we assume that it will follow the same concept as the 2D and 3D. Okay? So, if we go back to the formula here, we are saying that if the values are greater or equal to 0, we consider them as positive. Otherwise, we call it negative sample. So this is called a step function, which read the output. The output is 1 if the value of the formula is greater than 0 or equal to 0. Otherwise, -1. So when we look at the topology of the perceptron, this one is only, we have the input. This is your input. This is your output, because we only have positive and negative, right? So we will look at only one neuron here, one layer and one neuron. Okay. So the task is to determine whether, given the input, we have positive or negative sample. So this is the weight that we are estimating during the training session. Okay. So this is the sum up of all the value that we have for x1, x2, and so on. And this is the bias. This is the bias. The bias is used to shift the line or the piece of paper in the 3D to improve the accuracy. So we will have two classes, positive and negative, depending on the value of the output of the function. And we will have the weightage, sometimes they call it slope parameter. Okay, so this is the one that we will estimate during the training session. Okay, they call weightage, weights. And we will use this formula to consider whether they are positive or negative sample. So let's suppose we have this example. So suppose we want to predict whether a web user will click on an advertisement for a refrigerator. So we have 4 features here, and they are all binary feature, means on and off, whether they tick or not tick, okay, or not tick. So we have 0 or 1, okay? And let's suppose we have estimate the value for the weightage of each of these during the training as 2, 8, minus 15, 5, and the bias is minus 9. So if we use this formula here, and then let's suppose we have one guy click on this, which is the yellow one. So that means the rest is 0. This is 0, 0, 0. So this is 1. Okay. So only this one will be computed minus this. So this is 8 minus 9. So we have minus 9. So if a customer search for review, so there is no guarantee that he will buy the whether a web user will click now. Suppose we want to predict whether a web user will click on the ad for. This is a web user will click on advertisement for refrigerator only. Okay. So if he click on search review, so that there is no guarantee that he will click on the advertisement on refrigerator. Okay. If we have another example here, if he click search review and also search repair, so we will have this value 1. So there is a high possibility that they will buy and they will click on the advertisement on refrigerator. Okay, so since this is positive value, the prediction is yes. Okay, so that means we have 1, 1, 0, 0. Okay, if we have these two, search review and click ad before, so yes. So if the guy has clicked the advertisement before, then the chances of this customer clicking on advertisement related to refrigerator is high also. So if we have this, you see if this guy has recently bought the refrigerator, so minus 15, so a big deduction here. So the total is minus 11, so prediction is no. If someone bought a refrigerator recently, they probably are not interested in shopping for another one at any time soon. Okay, so if a guy did not do any of this, so minus 9. So since most people don't click it, the default prediction is they will not click on the advertisement related to refrigerator. So that's how do we do prediction, a simple one. So during the training process, what we want to do is we want to estimate the weightage of the variables. So in this one, the perceptron algorithm learn the weights by first initialize all weight w to 0, and then iterate through the training. They look at which one is misclassified, which one is correctly classified. So what happened is that if the prediction was wrong, they will modify the weight by using the update rule. So if your aim is to be a negative sample, so you will try to change the signage of your weight to negative. Okay. For example, if your actual product is negative. No, your actual class is negative, and then the prediction one is positive. So what you want to do is you want to update this to be you want to update the weightage so that this symbol will turn to be negative. If the actual instant is positive but predicted as negative, so you want to use the update rule to move this one to be positive. Okay. So we will repeat step two number some number of times, depending on how many misclassified or correctly classified sample that we have. Okay. So what is the update rule do? Okay. So this is what I meant just now. If currently if classifier predict an instant was negative, so you predict the instant as negative, but it should be positive. The actual one is positive. So what you want to do is you want to adjust the weight so that this function value move towards positive. So you want to change this one to be positive because the actual one is positive. Okay. And if the predicted value is positive, but the actual one is negative, so you want to change this one to be negative. Okay, so this is the update rule. So how can we do this? How can we adjust the weight so that your misclassified sample can be correctly classified after adjusting the weight? Okay. So look at this formula. This is the weight of the feature J. This is the true label. This is the actual label. This is the predicted label. And this is the value of feature J. Okay. So you see this symbol is basically updating the weight of your feature J. Okay. So if we take this formula here, okay, why this is your what? This is your actual, right? And this is your predicted one. And this is minus, and this is the output, the predicted one. Okay. Okay. So if your actual symbol is positive, minus, and you predict them as negative, let me change the symbol to be number. Okay. So we have this. So the value for this one would be positive too, right? So that means we are changing the weight to be +2. Okay. But if the actual one is negative, because this will move your symbol negative here to be positive. But if your actual symbol is, or your actual class is minus, negative sample, but your predicted value is this, so you will get -2. That means you will update your weight to be minus. Okay. Okay. So Let's assume this is 1. I'm repeating again what I have mentioned just now. So this term is 0 if we have both predicted and the actual class is the same. So if they are the same, so no weight update will be applied. Okay, no change is made. Okay, but if the prediction is wrong, so for example, this is your actual one, this is your predicted one. So you want to move this one to be positive. So you have to add +2. So this is achieved when we have +1 minus -1 from here. Okay, but if your actual is negative, but they are predicted as positive, you want to move this one to be negative, so to become -2, so it will be reflected in here -1 minus +1. So you have -2. This is minus +2. Okay. So this one will be automatically updated depending on which one is misclassified. The sign of this term indicates the direction of the mistake that we have. Okay, so this one is we want to move towards negative. This one we want to move towards positive because this is the actual symbol that we have. Okay. Okay, so if the prediction is wrong, so that means this is what term is +2 if your actual one is positive, but the predicted one is negative. So we want to +2 so that this one moves to the positive. Similar to when we have when the actual one is negative, but we are predicting them as positive, so we want to move them to be negative, so we have to change the weight to be -2. So this is the way on how they can adjust the weight of your variables. Okay, so when we translate this one into a program, so this is your pseudocode. So what happened here is that we get an x and y. So we will update the weight for this one. If they're the same, there are no changes. Else we need to fix them. So they are saying that if the signage of the sum of weight times the input, which is the class, if the error is possible, this is what happened. So this is your actual class is positive, but they are predicted as negative. So you want to make it bigger. So that means you want to +2. If your actual one is negative, but your predicted instant is positive, you want to make it smaller. So how do you make them smaller? It's just by fixing this. Okay. So you make this W as -x. Okay. This is when you want to make it smaller. This is when you want to make bigger. Okay, so you will repeat this one until they're reducing the number of misclassified instance that we have. Okay, so what about the B? The B in our formula here, which is this one. So this is the intercept of the linear function when you have the variable value as 0. They are called the bias. Okay, so this is the formula that we have, and if we add 1 here, this is a constant value. If we add an extra feature to every instance whose value is always 1, then we can simplify them by writing this. Then we can update the parameter the same way as all the other weights. So the weight for this would be 1. Okay. So this is the example of linearly separable. We have this one is good. This one is not linear, because if we try to draw a line, impossible for us to draw a line. This is also impossible for us to draw a line that will separate positive and negative. Okay. So in this example, if the training instance are linearly separable, eventually the perceptron algorithm will find the weights, will optimize the weight such that the classifier gets everything correct. Okay. For example, if we look at this, 2 input and output Boolean neuron, it is possible to represent the N and O function here. For example, if this is your positive and this is your negative class, so we can use the N get to show that, okay, if you have 1 1, so 1 1 is here, so this is the line that we have. And if we have this value for your x1 and x2, so that means they belong to here. Okay, for the O function, also we can use here. So this will be able to separate the positive. This is your positive, and this is your negative. So we can use also your or get function. But for this one, we will not be able to do the separation because we have both x inside here, and we need 2 line here. Similarly, if we treat like something like this, we want to separate here. So this is what we call nonlinear problem. So nonlinear problem, we have to use other method on how to solve this one. So we cannot use perceptron. Okay. So if the training instance are not linearly separable, the classifier will always get some prediction wrong. Okay, misclassified. So you need to implement some type of stopping criteria for when the algorithm will stop making updates. Stop making updates means stop making the adjustment of the weight. Okay, otherwise it will run in infinite loop. Okay, so usually this is specified by running the algorithm for maximum number of iteration and epoch. So this is why you need to specify the range of iteration and epoch number in your neural network. Okay, so that's the purpose of having this. But the main issue is, again, what is the optimized value for your epoch and also the iteration. Okay, so epoch refer to you want to do from the input to the output. So this is your input. So this is considered as 1 epoch. Okay. And iteration is how many time iteration you want to do this. Okay, so another thing that we have to know is the learning rate, because when we saw just now, we have, when we update the rule, we have +2 or -2, right? But we can adjust this one by looking at the learning rate. The learning rate here by default is 1, but you can change this one to zero point 0.2 or zero point 0.1. Okay, this is the size of changes that you are making, but you can make it smaller. For example, you want to times with 0.3, 0.3. So that means your the changes is made according to the learning rate. Okay, so we can make it smaller or bigger, or maybe you can times with 2 again. Make it big. Okay, so this is another thing that we have to consider when you are using neural network. What is the optimum value for your learning rate? So no, in most cases they use 0.001, 0.01, or even 0.00001. So this is the size, how small is the changes that you want to make, so that you can have the incorrectly classified instance to be correctly classified. Okay, so this is the issue, how to choose the step size. If n is too small, the algorithm will be slow because the updates won't make much progress. Too small. But if it's too large, then you will miss the bus stop, overshoot, and may cause previously correctly classified to become incorrect. So this is another issue that we need to tackle when we want to use neural network or the perceptron. Okay, so this is the example. This is the training, and this is the testing. So this is how they move the line, and they adjust the line by adjusting the weight of individual features that we have. For this one, we only have 2 features. Okay, 2 features, X and Y. No, X1, X2. So Y is your output. Okay. So you notice that, okay, this is okay already, but then when you overshoot, you will have okay, this is, we have the first iteration, we still have misclassification here. So the second iteration, they have adjusted, and it moved to the right, and now we have completed. Okay, in summary, we have studied this one. So this is the prediction function that we use. We look at the signage only and not the magnitude of your function. We also learn how to initialize the learning process, in which we will apply the update rule depending on the result of misclassification, and we have the learning rate here. Okay, so we will repeat this one until we have all the instant correctly classified, or it reach the number of epoch and number of iteration. Okay, so for the multi-class, so basically what we have to add is, we need to add this, because this is for binary 0 or 1, and this is for multi-class. Okay, so what happens is that it will do something like this. If it belongs to this class, so this is 1 0 0 0 0. So if the input belong to this class, so the rest will be 0, 0. Okay, so that's the differences between simple perceptron and multi-class perceptron, but the algorithm will be all the same. Okay, let's take a look at the some of the practical that we can do for the perceptron function in R. So we will use the iris data set containing 50 samples. So in this data set, we have 4 features. And we have the length and the width of sepal and petal in centimeter. And we have also the class here. Okay. So for this example, we will try to classify the Sentosa and vesicular species, because remember that the example that we have now is for binary class, so we will have 2 classes only, so we will take these 2 only. Okay, so to load the data set, we just type data iris. So this is coming from the library of the R software. Let me switch to R software. So we are getting the data from this. So if we look at the structure of our iris, so we have 150 observation, 5 variables. Okay, and we have 4 the numerical values and also the class. And then what we will do, we will only take column number 1, column number 3, and also column number 5. And this is, we only take 100 of them. So this is row, this is column. Okay. We only take 2 of them because we want to have 2-dimensional and able to see in the graph later on. So we take the sepal length and also the petal length. And then we look at the, if we look at the sample for this, so we only have this, right? So this is our 3 column that we have. Then we will rename this one as, to simplify the name here, the sepal length and also petal length and species, we just rename them. So now we have a simple column name here. Okay, so this one is just to rename your column. Okay, and to plot them, we use the ggplot2. Okay. It's okay, it's warning. So this is our nil. So our objective is to draw a line here, not separate these 2, the Sentosa and vesicular. Okay, and if you look at this one, okay, so what we want to do is we want to draw a line that will separate this 2 sample. No. First we define a distance. So this is used to calculate the distance. We use the Euclidean distance here. So basically we are taking the sum of square of the differences between two, and then take the square root, and we return them as the Euclidean distance. And then this is the classifier. So what happened here is that we will if the distance is minus or below 0, so we classify them as negative, otherwise positive. So this is based on the formula that we have, and this is the distance from the plane. Okay, so given the x, the weight, and also the bias here, we will draw a line that will separate the line that we have in our data set. Okay, and this is the classifier that we have. This is the coding. So this is following the description that we have in the pseudocode. So basically, we will adjust the weight here, and also the bias here, and this is the iteration number of times, and this is the distance here. So basically, we are looking at how do we draw a line that will separate both positive and negative class that we have. So this is the function perceptron. Okay. Okay, this one will bind these two columns, the sepal and also the petal that we have. So if we have X, then we have this. So we combine these two columns. So given the input of this, we will look at whether they are positive or negative. So if they are the same, means they are positive, otherwise minus. Okay, so if they are sentosa, that means we treat them as positive sample, otherwise negative. Okay, so if we put y here, so we only have positive and negative. So we need to combine this one with the y, but we already have that one. So meaning that our x and y is coming from here. This is x, your input. This is your output y. Okay, so we will pass this one to the perceptron. Okay, classified here. Wait, missing some steps maybe. Or we missing this one. So this is the distance from the line that we have. So this is the classifier. We'll repeat again. Okay. So now we have able to train our perceptron given the x and y, and then we can draw them. We can plot them. Yeah. Missing this one again. Okay, I will repeat this one again. Okay, so this is the plotting that we have, but not very clear. The number is 1 and 2. Okay? But if we draw a line here, we make it bigger. So we make it bigger here. So that is the positive. This is the negative one using the red. Okay. And then we will draw this line. So this is computed based on our previous formula here. We find the slope and also the interception when all is 0. And then we will draw this one, the line that will separate them. Okay. So the green line here indicate the best line that will separate the positive and negative sample that we have. So this is the one of the example. Okay. Any question? If you're okay, can you type number 3 on your screen? What's up? Okay. If you missed the first session of this class, you can view back the recorded session for this. Okay, now we move on to the second part of the lecture today. We look at the multi-layer perceptron. So for the multi-layer perceptron, um, this is not referred to a single perceptron that has multiple layers, but rather it contains many perceptrons that are organized into layers. So basically we have a few layers. So this can be used to treat the nonlinear problem. A multilinear perceptron are extremely useful for complex problem. So they call it multi-layer perceptron. Okay, and they can be used both for regression analysis and also classifier algorithm. So they can be used for speech recognition, image recognition, language translation, and many more. And it's proven that the multi-layer perceptron is a very good algorithm. Okay, so the function that we are looking here is the multi-layer perceptron. They have a few hyperparameter setting. So we have the input, we have the output, we have the size, the number of units in hidden layer, maximum number of iteration. Okay, the activation function of all hidden units. So in the neural network lecture, you have covered the activation function. This is for all the hidden unit. This is all the output. So remember that we have the input here and then connected to the hidden and then connected to the output. So this is the hidden layer. This is your output layer. Okay. And also we have a matrix with input to test the network. So you have input and also we have the corresponding target. Okay. So these are the parameter for the multi-layer perceptron. Okay, let's try to run this one. So we use the same data set here. And then we need to install this one to get the multi-layer perceptron. And then we have to upload into memory. Okay. And then, okay, and then we are getting one to number of row. So this is the maximum for the iris. And then we know the number of row that we have, and also one to number of columns. So before I go this, let me show you what we will be getting from this individual one. So this one will give you the number of row. Okay. So this is the total number of row. So we have 150, and this is the ID for the column. 1, 2, 3, 4, 5. Okay. So basically this one will be shuffled. Okay. We shuffle this. So if we look at, so now we are looking at the iris for column 1 up to 4 only. Okay. So this is the one. You see the row ID here, they are all shuffled. And then we are only displaying 4 column here, 4 column. And this is blank, saying that we are showing all the row number. Okay, and this is to capture the label. So we are getting the label. Okay, this is for all row. This is only for column 5. Okay. So if we look at this, the value for this, we have the label. Okay. So remember that this is the dummy variable. So if we have 3 unique values, so that means we will have 3 bits to represent them. So this is the decode class label. So what happened is that for the output, we will have 3 output. So one is for Santosa, one is for the versicolor, and one is for the Virginica. So we have 3 output. So depending which one will be turned on, that one will be the class of your input. Okay. So what we want to do is we want to combine your input and your output here to the multi-layer perceptron. Okay, for this one, we split them into training and testing again. So this one, we have all the values, we have all the target, and the ratio is 0.15. That means 80% for training, 15% for the testing. Okay. And also we have to normalize because you look at the values here. Some are small, like the fourth column. Some are big, like in the first column. So we will normalize all our value here. So if you look at the Irish, oh, yeah, so we have this. So this is our input already, normalized already, and this is our target. Okay, yeah. So we have the input here. This is your testing. This is your testing. This is your training. So we have divided them into 85%, 15% testing. Okay. Okay. Now we will build the multi-layer perceptron. So what happened here? We pass the x and the y here. So this is the number of hidden layer. Okay. This is the learn function parameter. If we look at the slide in the beginning, this is the sequence x, y, and then the size, maximum number of iteration, hidden activation function for the hidden, and also the activation function for the output, input test, and so on. Okay, so maximum iteration, input, and target. So we build this model. Okay, so once we model this one, so we look at the summary here. So this is basically the weight that we have. Okay. So let me make it big. Yeah. So we have all the weight. Okay. So we have input. We have hidden layer, and also we have the output here. Okay. So these are the bias for each of the node that we have, and also the weight. Okay. So this is the activation function for your input. Yeah, but very hard to visualize here. But can we also can look at the weight matrix. Okay, so for hidden 2, 1, 2, 2, and up to 2, 5, so that means we have 5 neuron, and we also have the 3 output here. So this is the weight, and then this is just to plot the error based on the training one. Okay, so we have 15 number of iteration, and we have the black one is the actual one, and the red one is the training one. So we have no. This is the weight. Yeah, the weight of sum of square. Okay. So for testing, we have to do the prediction here using the model, and we provide the testing data set. So this is your model. I use the model to predict your input, and output is here. So this one is just to look at the regression error that we have. So we're supposed to have the black one, tapi we have the red one. Okay. And we need to draw the confusion matrix to know the percentage of accuracy that we have. So over here, we only have 3 error, 3 plus 2, because you have 3 target, 1, 2, 3, and these 3 plus 2 are the error. So this is for the training, and this is for the testing. Okay, for the testing, we have 1 error here. So 1 out of 23. So the percentage is accuracy is 95.6. So quite high, but this, yeah. And also we can draw the receiver operator characteristic. But this one doesn't tell you much because our accuracy is high already. So basically we want um, to maximize the area that we cover here. Okay, so this is when you have what we call it. This is true positive rate. True positive rate. You want to have 1. So that means all your positive rate should be classified as true positive as well. So we want to maximize here. Okay. So 1 is for your training. This is for your testing. Okay. Sometimes we have curves, something like this or like that. So the objective is to move the line up to here to maximize the uh, accuracy. So if you have a graph something like this, you have a very good model. Of course, the example that we have here is a very simple one, and we have a lot more complicated data set. Okay. This is the last one. Okay. So this is we are looking at the model itself. So this is our target, and this is our prediction here. Okay. So we have this is the error that we have, which and we use this symbol here. A pattern is recognized as classified correctly. Okay. So method, this is the sample that correctly classified. Okay. So the method derive its name from the commonly used default value IH. So this is the default value for this I. The output of all the output unit is less than this value, and this is for the h value. Okay, so for this session, we have looked at the binary classification and also the multi-class classification using multi-layer perceptron. So we discovered the linear separable classifier and the function this concept applies. We also learned a simple perceptron implementation function in R environment. So you can run through the experiment here, and then we learn how to train a model for a multi-layer perceptron. Okay. Any question? Okay, if you're still there, can you type number 5? Ada yang lambat nih baru masuk.